All right, everybody, welcome to Earth Science. Let's think a little bit more about volcanoes, like within the context of igneous rocks, now that we understand what they are a little bit. What goes on with these things? So, we're going to make this a little bigger. There's different types of volcanoes. Different volcanoes are going to look different. If you did the first part of this lesson, if you had free time last week, you saw some video of lava in Hawaii, and it kind of flows like a river. If you've ever seen any of that, you've got, you can have these like red rivers of lava flowing by. You can come reasonably close to like checking it out, to watching it. Other times, like think of Vesuvius Pompeii, they're like these giant explosions, right? So why is there a difference in this? What it comes down to is that not all magma/lava is the same. The type of volcano comes down to the composition of the lava. What is in there that erupts, and what's it like? And that's going to make your volcanoes look much different. And the big thing, the big X factor in all of this is SI, the amount of silica in the magma. That determines its viscosity. So let's just real quick remember that if you're over here on the felsic side, it's rich in silica. If you're over here on the mafic side, not so much. So that drops off as you go down that composition spectrum, whatever you want to call it, right? The further you go to the right, the less of that there is. Okay. So what does that mean for us? It changes the viscosity. Viscosity is a fancy pants term for resistance to flow, how sticky it is. Think of water versus like maple syrup. If I dump or molasses, if I dump those both on the counter, which one's going to flow more easily? So resistance to flow, in simple terms, how sticky is not a great word to use because you think like maple syrup sticky, but like it's kind of the best I got. Okay. So if we have this very sticky lava, we end up with what we call a composite volcano, or if we have a very runny lava, we end up with what we call a shield volcano. All right, so now we're going to draw both of these very, very simple drawings. Do not panic. Sorry, I had this set differently. Okay, so I'm going to start with a composite volcano, which I'm going to draw down here to say that you kind of get a steep-sided, cone-looking volcano like that. I should probably have images ready, but all right. Steep sides, the Pacific Northwest, a whole bunch of these, Mount St. Helens, Mount Hood, steep sides, mountains like that. Okay, and when they erupt, they can be pretty explosive. That differs from a shield volcano. Now, if you go up to the side of this thing, if you walked up to the side of Mount St. Helens, you can say that is a big mountain. You're going to say, I don't really want to climb that, right? Unless you're into it. They're large. They're big. It's a big old mountain, right? It would be a doozy to climb that whole entire thing. But that's large in a certain context. That's large to you as a person sitting there. Shield volcanoes are ridiculously large. And what they're going to look like, since the lava is more runny, when it comes out, it flows down gentle slopes more easily. So what we end up with is like really broad, much flatter volcanoes that absolutely dwarf Mount St. Helens ones. This one should honestly most likely be a little bit smaller even. In fact, it definitely should. You don't have to redo it if you want to, but I'll be a stickler. And that's probably still not that great to scale. All right, these are enormous. And an example, I'm going to say Hawaiian. All these pictures we're going to get. A whole entire island. That's the example I'm trying to come up with. So like you don't get that big dramatic mountain peak that you do. I mean, you can get little ones around some of the eruptions, but all in all, for the whole entire island, if you were to step back to an appropriate scale, it's going to look a lot larger. All right. And you also got to consider that the Hawaiian island is built up from the ocean floor. So like all of that, huge, 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 huge. And yes, there's only a couple spots where it's like currently volcanically active. You can see some fresh stuff down here. But that whole entire thing is all one shield volcano, one very, very, very large, reasonably flat volcano versus smaller guys like this that are, again, big old mountains. If you had to climb it, yeah, that's intimidating, but tiny compared to the whole entire size of the main Hawaiian island. And all the other Hawaiian islands, by the way. I mean, we'll have to look at that. We'll look at those a little bit more closely in the tectonics unit. But all the Hawaiian islands, wherever they went, all of the Hawaiian islands, that kind of being the remnants of one, were at one point over this hotspot. The entire tectonic plate has shifted away from it. So these are all shield volcanoes. These guys are all now dormant, and this is the currently active one. And eventually, we'll get a new one down here. You and I won't be around for it, though. All right, so how explosive is a volcano? These things blow their top like crazy, and they can be violent, deadly, like scary deadly, very dangerous, very explosive, and dangerous. Not a pretty way to go at all. Whereas shield volcanoes kind of just run and flow, not explosive. They do damage? Yeah. If you made it through all those videos at the beginning of the lesson, again, which is all dependent on you having enough time for it, you saw that they like leveled out a neighborhood to 3-ish years ago. They can be dangerous, but you can generally see it coming. It's not going to be this explosion of pyroclastics, and that's the big difference. They'll call these gray eruptions. They send, it looks like ash, and it is volcanic ash, but it's rock. It's finely grained rock, essentially. Very, very, very hot, and if that gets in your lungs at that, it's bad news. Okay. Look up, if you're morbid and you want to see some of this, look up pyroclastic flows. Over here, they call these red eruptions. Unless you're really in the wrong place at the wrong time, you can be safe from, and you can outpace. All right, so using brains, well, what's the composition of lava then? These guys, the composite volcanoes, and this went with the end of the rock lab, and it's a bit tricky to make these connections sometimes. So, like, think about it. Composite volcanoes with a very sticky lava that are high in silica, which we should have mentioned, right? High in Si, these guys being low in Si. So what's the composition of the lava? If you know your reference tables, you're starting to get some of this down wherever they went. If you're over here with the light colored rocks with the silica, these are your felsic volcanoes, whereas the very runny ones are mafic. So Hawaiian rock, you're going to expect to see be black. In fact, that is the correct answer to the lab. And Mount St. Helens rock, you're going to expect to be light colored. So again, that's the answer to the lab. If you want to go back and fix it. Let's check it in here. Maybe we're good to go. I think we are. So this is felsic. This is mafic. Excellent. Good work on igneous. That's officially the end. We'll move on to metamorphic next. No, sedimentary. We're going to move on to sedimentary next. Thanks for tuning in.